Okay, can you see the presentation?
Yes, looks good.
Okay. Hi, everyone. Um, this is what I want to talk about today. First, I would like to set out a goal on what I want to achieve, which is, as the title says, to enable full text search in an application with minimal changes to the application and minimal effect on the existing infrastructure. And I'll talk mainly about three topics: change data capture, what it is, what it's good for; stream processing, and how it can help us achieve our goal; and specific issues you might come across when indexing data into Elasticsearch using this technique. Also, let me tell a few words about me. I'm a software engineer at the Hazelcast Jet team. Hazelcast is in-memory computing platform, and it is composed of two products: in-memory data grid, which is a computing and caching solution, and Hazelcast Jet, which is a stream processing engine. And I'll talk about Jet a bit later. So now let's get to our goal, what we want to do. We'll take a typical enterprise application, CRUD application with three-tier architecture, using relational database for storage. And this application already has a search capability, but it's rather limited. And it's also easy to imagine that such application is hard to maintain because there is a lot of technical debt, and the knowledge about the internal workings of the application is long gone because some of the team members who developed the application have left by now. So you would like to do this with minimal changes to the application because it's risky to change the application, and also with minimal changes to the existing infrastructure. For example, you don't want to add additional load on the database by extending the search functionality. So, and we want to provide the search by using Elastic because it's a full-featured full-text search index, and it fits the use case nicely. So, as an example, I've taken the Spring Pet Clinic application. It's a well-known application to Java developers, and for those of you who are not Java developers or don't know this application, it's a simple CRUD application for managing owners of pets and visits of those pets to pet clinic. And it has we'll focus on three main entities, which are the owners, pets, and visits in our example. So let's talk about change data capture and what it is. It's a technique, and in the simplest form, it's about capturing changes made to the data and making those changes available for further processing. And you might be interested both into schema changes and data changes, or one or the other, doesn't really matter. And there are many reasons to capture changes. You might want to replicate the data to a different system, to a secondary storage, which can serve your queries better. This might be a different database or a search index or graph database or columnar database for analytics or anything. And there are many ways how to implement change data capture, ranging from implementations on the application layer itself, where you just add additional code path and send the changes somewhere else, or through network or a database driver, or it's possible to implement it directly inside a database using, for example, triggers or reading transaction or replication log. And the last approach, reading the transaction and replication log, is what we'll talk most about. So this approach is based on reading either replication log or transaction log, and it's usually easy to do because the database is exposed this replication log for either backups or synchronous replication or other uses, and we can leverage this as well. Usually there is minimal impact on the database, or it's very similar to basically enabling replication on the database. And it's low latency, meaning that you can get to, you probably won't get to low milliseconds, but you can easily achieve something between 100 milliseconds and 1 second from making the change to seeing the changes in the other system based on this technique. And you don't need any additional changes to the database, to the schema, or to the application logic to basically use this log-based CDC. There are also some disadvantages to this approach. And the first one is that if you don't have, usually you don't have the whole history, the whole log available, because it would take a lot of space to keep the whole transaction log for years and years of for the database. But this is easily, you can work around this by creating something or doing something called initial snapshot, where the CDC tool basically scans all tables sequentially and basically reads the whole database before starting reading the replication log. And the other issue or other problem that you need to solve or work around is undefined order of the change events that you receive. Usually you will receive the changes in the order of the transactions, but this order is slightly vaguely defined because there is no total, usually there is no total order on the transactions. The databases are free to reorder the transactions according to isolation levels. And also within the transaction, the changes to individual rows are not defined. The order between them is not defined because it's an implementation detail of the database. And if you make changes to 2 rows and one has a foreign key to another, it's not defined whether you will receive the main row or the dependent record. And you need to be able to handle both situations. So there are existing CDC solutions, change data capture solutions, and I would split them into 2 categories, proprietary and open source. And the proprietary ones are usually either made by the database vendors like Oracle or Microsoft, or are part of larger ETL solution. And for the open source one, they are usually made by large tech companies which develop those tools to serve their needs, and usually focus on single database or maybe a couple of databases. One notable exception is Debezium, which is developed by Red Hat. And this is open source library under Apache 2 license, and it supports MySQL, PostgreSQL, SQL Server, and MongoDB. And there is incubating support for Oracle, DB2, and Cassandra. So this supports the widest range of databases from the open source tools. And it integrates with Kafka and Kafka Connect. And typical Debezium deployment looks like this. You have your source database, and then there is a Debezium connector with Kafka Connect, and then you have a Kafka cluster, and then another connector which writes to your target system. So you need to have a Kafka cluster running, which is the biggest issue in my opinion with this deployment, because it's hard to maintain and run the Kafka cluster. You need the Zookeeper as well. The connectors are deployed as separate processes. So this is not really a simple deployment, but it works. So how does the change data capture works, or how does Debezium work? So for an example, if you issue this update to a table of customers, which sets a field first name to a new value, you will receive an change event with the following content. There is a schema field, which contains the schema of the particular table. And then there is a payload. The payload contains the state before the change or before the query executed and after the query executed. So you get both states before and after. And then there is additional information about the source. So that there is a database name, table name, and some additional fields I have omitted. And then there is also information about the kind of operation which was done. In this case, it's update. If it was a create, you would have the before field empty. And if it was a delete, you would have the after field empty, because there is no new state of the record if you do a delete. So let's talk about another concept related to change data capture. and it's stream processing. Stream processing is performing computations on data delivered as an unbounded stream of data. And changes from a database is an example of such an unbounded stream. Another examples would be changing price of stocks or user activity from a website, either going through sites or clicking on links and so on. Or another example could be data from sensors, for example, on an oil rig. So anything that's potentially infinite or basically comes in all the time. And the data is usually processed as they come in semi-real time. Typical latencies range from milliseconds to hundreds of milliseconds. And if you need good guarantees about, if you need strong guarantees about storage, then in worst case, you can reach a latency of seconds, but it's a rare case. And apart from reading and writing data, which is the typical, which is the most common operations, you need another typical operations that you do are aggregations, enriching the data, running machine learning algorithms, filtering, doing lookups or joins of the data. And examples of stream processing engines include Apache Flink or Apache Spark, which is originally batch-oriented, but with the latest versions, they have a streaming extension, and also Hazelcast Jet. So to quote from our website, Hazelcast Jet is a distributed batch and stream processing system that can do stateful computations over large-scale data with consistent low latency. This is a fancy description, but it's true. And it's open source mostly, with some connectors being source available. They have a very open license, but the license is not considered open source because it doesn't fit the definition. But the source is still available. And we have a range of connectors to various databases and systems. And we have a connector including connected to Elasticsearch and also Debezium. And I would say that the value proposition, one of the key value propositions we have is that it's very easy to operate compared to other systems. When you create a cluster on a network, it connects together, it discovers other members automatically, and it's much easier to operate, for example, than the Kafka cluster. So in Hazelcast Jet, you define a job using a pipeline API written in Java. And the pipeline API is similar to, for example, Stream API in Java. And it has a typical operations you would expect from such API, like a mapping, filtering, aggregations, and similar. And once you define the job using the pipeline API, you submit the job to a Jet cluster, and the cluster takes care of executing the job itself and distributing the job across multiple members and so on. So what I think is going to be interesting to this group is how we build the Elasticsearch connector for Hazelcast Jet. So first we had a choice whether to use the Elasticsearch Java client or whether to directly use the REST API. And in the end, we chose to use the Java client, despite the fact that it brings a lot of dependencies on Elastic Core, on Lucene, but it provides a familiar API to the users. And this is something that we wanted to provide to our users as well. So basically, when someone who already uses Elastic and tries to use Jet with Elastic, they have a similar API. So originally, we thought that the client will handle all network and Elastic node failures very well. And it does it for most of the cases, but it turns out that it doesn't cover all of them. And we had to implement a custom retry mechanism on top. And the typical situation where we need additional retry is when a primary shard in Elastic gets disconnected. And the client tries to connect to another node with a shard and tries to write the data to that node. But because the primary shard just disappeared, it can't perform the operation because no new primary shard was promoted yet. And it does this for all nodes in a very short sequence of time because there is no delay between those requests. And basically fails the request, and then we have to wait for a while and retry the operation again. And we also faced a issue with non-trivial setup for our QA, where we wanted to set up a cluster which handles failures quickly and without losing any data. And it's documented relatively well, but we still had to do lots of trial and error steps to basically set up the cluster itself, not the client, not the connector, but the cluster itself to perform the recovery in a way that we wouldn't stop for minutes waiting for the cluster to heal. And we also implemented something called collocated reading. So when you run Elasticsearch and Jet on the same set of nodes, Jet will distribute the job and read from Elastic in a way that it doesn't transfer any data across physical network. It will just read from the local Elastic nodes. So it will read all the shards and plan the job execution in a way that it executes only, or it reads data only locally. So now we have all the pieces together. We have a Spring pet cleaning application, which uses MySQL database. We want to put the data into Elasticsearch, and we want to use Hazelcast Jet with CDC connector and Elasticsearch connector to basically move the data and also do some enrichment inside Hazelcast, inside the Jet job. So this is the overall architecture of the solution, and if you compare it to the solution with vanilla Debezium, there is Jet cluster compared to the Kafka cluster. The Kafka cluster on the below image, on the bottom image, is missing zookeeper nodes. So there is one more thing to maintain there. And the connectors in the Debezium case are deployed as separate processes and separate JVMs. And in the Jet example, they are submitted as part of the pipeline or as part of the job, and they are run automatically by the Jet cluster. So this basically simplifies the deployment of such a solution using Debezium, and it's much, in my opinion, it's much easier to manage. So I have a demo prepared on the slides, and then I'll show all the steps on the slides, and then I'll show it live running, so we don't have to wait for all the commands to finish. So first, we'll start MySQL database using Docker. So this is the command. It will create the database. User will set a password, and we'll publish the database on a particular port. And then we'll get the application, the Spring Pet Clinic, using just Git from GitHub, and start the application. The application will also create a schema inside the database. So it will create the tables and populate the tables with data. And then we will enable CDC in the database. It's basically adding some permissions to the Pet Clinic user, to the user we use to connect to the database. And to set up Elasticsearch, we'll also use Docker. We'll start Elasticsearch in single node, and just that's the first option, the discover type single node. And the second option, it's just a tip to everyone who comes across this. When you run Elastic on your machine and you run out of space, or you have over 90% of your disk space taken, Elastic puts itself into something, into a yellow state, instead of a usual green state where everything is working as usual. And it will cause some issues with shard allocation and writing data to Elasticsearch. So this is just to disable this threshold, and it will stay green. And I'll be using the 7.9.2 version. I didn't have time to update to 7.10, which was released just, as Rich said, just a week ago. And we'll create a relatively simple mapping for the index, and we'll copy all the fields we are interested in into single search field, and we'll use this search field to search. The reason to do this is because there are other fields in the data that we will put into Elasticsearch, and we want to avoid searching all fields, for example, addresses or street names and so on. So we'll selectively copy only the fields we are interested in, which means the first name, last name, name of the pet, and description of the visit, or keywords of the visit. So just running this command using CRL will create the mapping for the index. And now the streaming job. So the first section creates the CDC source using Debezium connector in Jet. It basically just sets a couple of parameters like database address, port, user, and most importantly, the database name and database tables. And then in the bottom part, we create a pipeline that reads from the MySQL source and then maps the change events into POJOs, or plain old Java objects. It's basically just a simple object containing the data, and then enriches the descriptions with keywords. So it extracts the keywords from the description and puts the keywords into additional field. And then we want to write it into Elasticsearch. But there is an issue that we'll basically receive the change records as individual rows. So when there is an update to a pet, we'll just receive a single pet record. When there is an update to owner, we'll just receive a single owner. But we want to basically store the data as a single document, single nested document. So we need to join these records. And we need to handle the situation where where we don't have the order on the events defined. So we need to handle the situation where the pet arrives before the owner, despite the fact that you can't actually do it like that in the application. You need to first create an owner before creating a pet, but you might receive the data in different order. So we need to be able to handle it. And there is several options how to do this. So the first option is to basically do the join inside Elasticsearch using something called scripted observed. So this is a combination of update operation and insert operation, and there is going to be a different request for the owner type, different request for the pet type, and different request for the visit type. But the principle is the same for all of them. And it either creates a new document or updates the existing document, and it updates the data using this script. And in this example, I'm using the painless language, and there's on the right side, there is the script itself. The fields of the document are in the context._source. And we just add additional names from the request. And we also have to define a retry on conflict, because there might be multiple requests updating the same document at the same time, because the job executes the operations in parallel. But just retrying handles this situation really well. So there are two issues with this approach. And the first issue is that you will get partial documents. So when you just receive, for example, a pet, you will create a document which contains information about the pet, but it doesn't have any information about the owner. Whether this is an issue or not depends on the application, and you could potentially handle this inside the application. But as we said at the beginning, we don't want to do that. We don't want to modify the application too much. And it might lead to inefficient indexing, meaning that you will index the same document multiple times without actually needing to do that. So for example, if you received a visit and then a pet and then an owner, you should be fine with single indexing request, which puts all the data in one go in there, but instead it will be indexed 3 times. So option 2 is do the join inside Jet in something called stateful mapping step. It's basically a mapping step, but with a state, which is kept in memory. And typically you would split the events by type and then join, for example, the pet and visit first and accumulate the incoming records until you have the master record, which is in this case, like you accumulate the visits. And then once you receive the pet, you publish the pet, and then in second step, you do the same thing for the owner and pet combination. And you basically end up with a full owner document, which then you can write into Elastic in a single indexing request. And then option number 3 is ignore the data in the change events and just load the data from the database using database driver, and basically use CDC just as a notification to get the IDs of changed records. This will be very simple implementation, but it increases the load on the database, and we said that we don't want to increase the load on the database. And it will do multiple lookups for the same record again and again when there are updates, and we probably don't need that. So once we join the data somehow, either using the option number 2 or 3, or potentially you could also combine the option 2 and option 3, where you would keep not all the data in memory, but only some of them, and using some kind of a retention policy would remove the old records, and once you come across a record which you don't have in memory, you would load it from the database. So that's also an option, but again, the implementation is relatively complicated compared to this. So once you have all the data inside the owner object, you can write it to Elasticsearch. This is how you create a connector or sink, which is basically the target system or the place where you want to write the data from the pipeline using the Jet API. And you can, for people who are familiar with the Java Elasticsearch client, this will be familiar. So the REST client builder is from the Elasticsearch client, and the update request is also from the Elasticsearch client. And we basically transform the owner to JSON document using some JSON util and create the update request like this. And then in the pipeline, you just say that you want to write into this Elastic Sink, and basically you're done with you're finished with the job. So once you create, then you create a jar with this job and submit it to a cluster using a script, which is part of Jet. Provide parameters with the location of the database and location of Elasticsearch, and on the name of the index that you want to index into. And then we will change the application. So the change is really simple. There's a new method, search, which just uses Elasticsearch client to search for a given query. It uses a wildcard query. And then there is a simple change where we replace the call to the database, the previous call to search, which was just some search by regular expression with call to our service, and then which loads the IDs of the owners, and then will load the full records from the database itself. This is quite a common pattern, and the reason for this is that you might actually not have all the data in Elastic. If you have all the data in Elastic, you could potentially load it from Elastic and avoid the call to the database. But the call to the database is actually not expensive, because you just load one page of records by IDs. So this is very fast query. It's not like the query before that, where you use the regular expression on many thousands or millions of records in the database. So now I'll show this running live. So this is the Spring Pet Clean application. There are some sample data, and this is a list of all records. And if I search, for example, for Franklin, it gives me single result. And this is basically the scope of the search that they implemented before, that the application had before. It just searched in the last name. And now with our changes, I've basically done all the steps that I had on the slides before. So now I'm running the updated application. And if I search, for example, for George, it finds the same record, George Franklin, but it also finds a different record where we have the result, the keyword in the pet name. And just to see the update going through to the database and then through the Jet job, I will add a new pet bird called Polly. So I can see that there's another bird called Polly. When I try to search for this, I should get the result. Yeah, I can find the result. If you look inside, so this is Elastic running on my local machine, and we should see the documents there as well. Yeah, so this is how the document looks like. So it basically just the first name, last name, and the pets, and so these don't have any visits, so there are no visit records. And this is the job running, the Jet job running, and I have two log outputs here at the bottom. So the first one is the change event the job receives from Debezium. So there is the information about the new value. So this is slightly stripped out compared to the example I had on the slides. This contains only the new value. So I have the operation here. It says create, and there's the name Polly, and then after going through the pipeline and the enrichment and everything, this is what actually goes into Elastic. So this object, which is then transformed to JSON using the Elasticsearch connector. And this is basically everything I have. So are there any questions?